Ancient stonework could match the precision of a modern laser cutter. It wasn't magic. It was a forgotten science. Our ancestors, without electricity or computers, they developed 25 distinct methods. 25 ways to carve stone with near-perfect symmetry. They had a hidden language of geometry and patience. That's what built the world's most enduring monuments. How do you transfer a master design onto a mountain of granite? There was a simple tool that used sunlight to check a statue's balance. The answers are in these techniques. They blur the line between art and advanced engineering. They show a level of collective genius. It still whispers from the quarries and temples. Our drive for perfect symmetry. What does that tell us about who we are? A sculptor stands in a quarry. He's not holding a chisel. He has a ball of string and a small clay figure. That's where symmetry began, long before the first strike. It began with a grid. The Egyptians perfected a system, a reliable system. It could take the features of a god from a model in your palm and put them onto a mountain of granite. They called it the grid and template method, their first secret to flawless replication. The original blueprint. A master artist would make a perfect small-scale model first. Clay or plaster, every detail was finalized there, every proportion. Then they'd put a precise grid over the model's surface, fine lines in red ochre. That same grid, scaled up dramatically, was painted onto the waiting stone block. The scale was the key. If one square on the model was the width of an eye, that same square on the block might be the width of a forearm. They used simple tools, proportional dividers, two pointed legs with an adjustable pivot, to transfer measurements from the small grid to the large one. Point by point, square by square, the outline of the colossal figure emerged, a painstaking mathematical process. Stonemasonry historian Dr. Elena Vance explains the grid wasn't just a guide. It was a shared language for perfection. It let teams of workers under a master craftsman work on different sections of a single statue. One team could rough out a shoulder. Another could work on a knee, and because they followed the same scaled coordinates, every part would align perfectly when they met in the middle. Take the Great Sphinx of Giza. Its serene, balanced face, carved from the living bedrock, that didn't come from guesswork. Its harmonious proportions, the exact placement of the eyes and mouth, were almost certainly plotted using this grid system. The faint red lines of ochre archaeologists find on unfinished monuments are the ghostly fingerprints of the process. This method turned ambition into achievable geometry. It proved the most monumental art started not with brute force but with meticulous planning, the foundation for all other carving methods. The grid had a limitation. It worked for drawings for things that were flat, but a sculpture has depth, the curve of a cheek, the angle of a shoulder. You need a three-dimensional map for that. Which brings in the second method, a device very clever. It feels like something from a Renaissance workshop, but it's older, the precursor to the pointing machine. It was a tool, really a bridge between art and early engineering. It took symmetry out of guesswork and into mechanical replication. Imagine the instrument. 3 adjustable rods fixed together to form a rigid, 3-armed pointer. The principle was simple. You'd place it against a finished master model, a small plaster statue. You'd adjust the 3 arms until their sharp tips touched 3 points on the surface. The tip of the nose, the corner of an eye, the curve of a lip. Then you'd lock the arms, that exact 3-dimensional measurement preserved. Then you'd carry the tool to your rough stone block, position it. Where those 3 tips touched the stone, you'd make a small, precise mark. That mark was the exact depth and location transferred from the model. You'd repeat that hundreds of times, thousands of times, mapping the entire surface, point by measured point. Archaeologists have found evidence at classical Greek sites, not the full wooden frames, those decayed, but the metal parts, bronze calipers marking tools that worked on this exact principle. These weren't just measuring devices, they were duplication machines. The charioteer of Delphi, with its serene expression, its perfectly rendered drapery, that's a testament to the method. That lifelike calm, that proportion, it wasn't just inspired freehand work, it was the result of a meticulous point-by-point transfer from a master model. It tells you something about classical art. The highest value wasn't just artistic expression, it was exact, harmonious replication. The goal was to capture an ideal form, to monumentalize it. This mechanical aid was the silent partner in that. It ensured the vision in the master's mind could be recreated in stone, not just once, but with perfect consistency. This was symmetry achieved not through intuition alone, but through a repeatable process, almost a scientific process. A statue is one thing, architecture is something else. To get perfect symmetry across dozens of identical parts, you need a process, a simple one, relentless, the abrasive string saw. Imagine a team on the Nile bank. They don't have a massive saw blade, they have a leather cord, they loop it around a granite block, they coat it in wet quartz sand, then a rhythm starts. Back and forth, this wasn't a quick cut, it was a patient grind, an abrasion. The hard quartz particles in the sand, dragged by the cord, became millions of microscopic teeth. And slowly, inevitably, they'd wear a channel, perfectly straight, smooth, right through the stone, like using a wire to slice through a giant block of cheese, but with the patience of a geological process. That method changed everything for symmetry in architecture. Think of a Greek temple. Its beauty is in the rows, identical column drums stacked perfectly. Or the massive lintels above doorways, perfectly rectangular. To get that, you need stone blocks with faces that aren't just flat, they have to be parallel. Their dimensions have to match exactly, so they fit together without a gap. The abrasive string saw made that possible, and the sand was critical. As materials scientist Aris Thorne points out, the specific quartz sand they chose mattered. Its consistent hardness, its sharp grain size that created a predictable, even cutting action. So as the team worked, the cut progressed at a uniform rate. No uneven dips, no curves to ruin the joint. The process itself was a feat of labor, coordination. One team pulls the cord one way, another team pulls it back. A third person constantly feeds fresh slurry into the cut. Wet abrasive, the cord would wear down, of course. It needed replacement, but they managed that. They learned to keep a steady tension, a steady rhythm, and that consistency in motion became consistency in the cut. The result was a face on the stone so flat, so true, that when placed against its neighbor, they'd fit. With astonishing precision, that's how you get those interlocking joints in monuments, joints so tight you can't slide a piece of paper between the stones. The proof is in a place like the Serapeum of Saqqara in Egypt. Enormous granite boxes there, each one weighs tens of tons. The lids fit their bases with a seal measured in fractions of a millimeter. The interior corners are sharp, the surfaces are flawlessly flat. That geometric perfection almost certainly came from abrasive sawing. The method shows an ingenious, practical grasp of material science. They weren't just cutting stone, they were using the inherent hardness of one natural material, quartz, to master another. Symmetry achieved through friction. Through patience and through an understanding of how the world works at a granular level. The surface was smooth from the string saw, but not perfect. For that final mirrored finish, they used a different rhythm, not pulling a cord but a steady tap of stone on stone. In the quarries of Aswan, the air hummed with a constant low percussion. Like 10,000 gentle hammers, that was the sound of diorite ball pounders at work, pecking symmetry from the heart of the mountain. Diorite is harder than granite. They shaped it into smooth, fist-sized balls. Teams of workers would hold these balls and strike the granite surface, not a crushing blow, but a controlled, repetitive tap. Each impact crushed a tiny grain of the granite. Millions of these tiny impacts, guided by a master's eye, slowly wore the stone down to the desired plane. This was the pecking method, brutally slow, but it offered something brute force couldn't: absolute control. A worker could feel the stone's resistance, adjust the angle, follow a pre-marked line with precision. It was a conversation between the craftsman and the material. After Pecking created the rough form, the grinding began. They used slabs of sandstone or other abrasive stones. Often with water and quartz sand as a slurry, they'd rub these slabs in long, even strokes across the surface, starting with coarse grit, then moving to finer grades. A process of incremental refinement. The water was crucial. It kept the abrasive slurry moving, cooled the stone, and suppressed the deadly silica dust. This wasn't just about a finish. It was an early, instinctual understanding of workplace safety. The goal of this marathon process was often the obelisk. A single, towering needle of stone meant to catch the first and last light of the day. Its four faces had to be flawless, perfectly flat, and precisely parallel. Any deviation would be glaring against the sky. The unfinished obelisk in Aswan is the world's greatest classroom for this technique. Still attached to the bedrock, it shows the precise channels carved around it by teams with diorite pounders. Its upper surface is a frozen landscape of peck marks, a testament to the work in progress. It was abandoned because of a flaw, a crack in the stone, but it remains a perfect snapshot of the patience required. Modern quarrying experiments have shown something. This peck and grind method, for all its apparent simplicity, allows for a level of surface control that power tools sometimes struggle to match. Because you're removing material so incrementally, the risk of a catastrophic split or an uneven surface is almost zero. The symmetry emerges not from a single dramatic act, but from the accumulation of countless deliberate choices. For these cultures, the perfection of the final form was worth a near inconceivable investment of time and energy. The monument wasn't just an object. It was the physical crystallization of that collective patience, a testament written not in words but in the mirror-like face of polished stone. The sound changes. From the pecking hammer to something sharper, more deliberate, tap, tap, tap. It's not for shaping, it's for drawing on the stone. In the low light of a rock-cut temple, a carver leans in. They're holding a metal chisel, not a mallet. They aren't carving a form, not yet. They're writing its future into the stone. This is incised guideline chiseling. The method where symmetry was committed, irrevocably, before any bulk stone was removed. Medieval masons called these lines the soul of the work, the absolute blueprint. It was a process of focus, profound focus. Using a hardened copper or bronze chisel, the artisan would hammer a groove, a V-shaped groove, into the stone's surface. They followed a charcoal sketch, but this was more permanent. This line was the final decision. A weighted cord often hung nearby, a plumb line, to ensure every vertical guideline was true. True to gravity, the central axis of a deity's face, the outer boundary of a gateway, these were locked in first. Different chisel points made different depths. A fine point for the curve of an eyelid, a broader one for the line of a jaw. This wasn't artistry yet, this was architecture, architecture for an image. The foundational geometry, the geometry every subsequent cut would obey. The importance of this step, it can't be overstated. Once you begin removing stone, there's no putting it back. A misplaced deep cut could ruin an entire block. Months of labor. The incised lines were the guardrails. They prevented error, catastrophic, irreversible error. For a master with a team of apprentices, these grooves were a shared language. The master would incise the primary lines, the essential boundaries. Then apprentices could work within them. Roughing out the interior volumes, knowing exactly where to stop. The lines were the law. Look at the floral patterns on the treasury facade in Petra. The symmetrical rosettes, the vines across the sandstone. That mirrored perfection almost certainly began with a master layout artist incising the key lines. How did they ensure one side mirrored the other? They likely used a simple technique. They'd incise the central axis line with absolute precision, then use a compass or a measured chord to mark key points equidistant from that center on both sides. By connecting those points with incised lines, they created a mirrored framework. A dance of geometry made physical. This method represents a critical moment, the transition from idea to plan, an immutable plan. It turned a blank stone face into a guided canvas. Every curve now had a path, a predetermined path to follow. The symmetry was no longer a hope. It was etched into the skin of the mountain, waiting to be revealed. The incised lines gave them a plan, but for a sprawling empire, a plan isn't enough. You need production. How do you create perfect, identical beauty for 100 temples, 1,000 tombs? The answer was a clever twist on an old technique, a variation of lost wax casting, but adapted not for metal, adapted to create the ultimate stone carving tool. A reusable mold. This was industrial scale symmetry. Picture a workshop near a major Roman city. The goal isn't one masterpiece, it's hundreds. They need to produce thousands of identical acanthus leaves for a temple frieze, or perfectly uniform rosettes for a series of official sarcophagi. Doing each one by hand would take lifetimes, so they industrialized the process. They turned art into a system. The method began with wax. A master sculptor would create a single, flawless model, an acanthus leaf, a goddess's curl, an intricate knot. This was their masterpiece in wax. Then they would encase this wax original in a special fire-resistant material. This wasn't just clay. Studies of surviving artifacts suggest it was a composite. Finely ground clay, sand, sometimes crushed pottery or grog. This created a mold that could withstand intense heat without cracking. The sealed mold was then heated. The wax inside would melt and be poured out or simply burn away, leaving behind a perfect, empty cavity, a negative space that held every delicate detail of the original wax model. This cavity was the key. Into it they would pour a slurry, sometimes a plaster-like mixture, sometimes a finer ceramic slip. When it hardened, they would break the outer mold away. What remained was a durable, positive copy of the original. But more importantly, that fired clay or stone positive became the master mold for production. These master molds were engineering marvels in miniature. They often included tiny vent channels carved into them. These vents allowed air to escape when the mold was pressed into soft stone or when a new slurry was poured, ensuring the material filled every crevice for a perfect impression. Now, a worker didn't need to be a master carver. They could take this durable mold, press it into a prepared surface of soft limestone or apply an abrasive slurry and create a perfect impression. Over and over, the consistent, machine-like perfection of the rosettes on Roman sarcophagi, row upon row of identical floral patterns, strongly suggests this mold-based approach. It tells us something about these empires. There was a massive, standardized demand for beauty. Sacred art and imperial propaganda needed to be consistent, recognizable and flawless across vast distances. This method ensured that a temple in Gaul and a tomb in Syria could feature the same perfectly symmetrical decoration. Speaking a unified visual language, it blurred the line between handcraft and early mass production. It meant complex, beautiful forms were no longer the sole domain of the elite or the singular genius artist. They could be replicated, making symbolic beauty a common, expected feature of the built world. The symmetry was no longer just in the object, it was in the very system that created it. A system designed for infinite, perfect repetition. Even the most precise mold still needs a perfect surface to start from, so they turned to something much stronger than any hand tool. A force that could carve stone not by hitting it but by washing it away. That's the seventh method: water jet assisted abrasion. It's where ancient engineering meets a basic truth. Water under pressure becomes a blade. The idea is simple. Instead of pulling dry sand across stone with a cord, you mix that sand with water to make a thick slurry. Then you direct that slurry under pressure through a narrow opening, a focused jet. What you get is a cutting stream of liquid sandpaper. It can carve a clean channel or drill a perfectly round hole, and it does it with incredible speed and symmetry. You see hints of this in some old texts. Egyptian records describing tube drilling often mention a constant feed of abrasive and water. The actual setup was probably clever but accessible. They'd use a hollow reed or a thin copper tube as the nozzle. That tube was loaded with coarse quartz sand, then attached to a simple bow drill to spin it. But the key was the water. A second person, or maybe a cleverly placed container, would trickle water down into the cutting area. That did three important things. First, it mixed with the sand right at the point of contact to form that efficient cutting slurry. Second, it flushed away the ground-up stone debris, which kept the cut clean and stopped the abrasive from clogging. Third, it cooled the stone and the tool so heat wouldn't cause cracks. The evidence for this is locked in the stone itself. If you look at core samples from ancient Egyptian sites, like the ones from the granite sarcophagus in the Great Pyramid, you see these stone cylinders drilled out by ancient workers. They show clear, concentric grooves spiraling down their length. Those grooves are the signature of a tubular drill spinning under constant pressure, fed with a consistent abrasive slurry. The grooves are uniform, symmetrical. They point to a steady, controlled process, not haphazard chiseling. The method's potential gets even more staggering when you think about scale. How do you drill a massive, perfect hole through a multi-ton block? The answer might be combining this technique with simple hydraulics. Picture an animal skin bag, a water skin, suspended above the work, filled with the abrasive slurry and then compressed, not by a machine but by weights or by the steady pressure of a worker's foot on a bellows-like apparatus. That would create a sustained, directed flow of the cutting mixture. It turns a laborious manual process into a semi-automated one. The worker guides the tube, but the pressurized slurry does the cutting. Then consider the stone anchors at Baalbek. Among the largest worked stones on Earth, these megaliths have perfectly cylindrical holes, bored straight through granite in a way that defies modern explanation. The cleanliness of these bores, their precise circular symmetry, raises a question. Could a mastered version of this hydraulic abrasive method be the answer? A method where water wasn't just an aid but the primary cutting force, harnessed and directed with purpose. This technique is a leap in thinking. It's no longer about stone working against stone. It's about using the fluid dynamics of a simple mixture, water and sand, to achieve a level of precision that feels almost modern. It merges the simplest materials with a deep, almost intuitive grasp of natural forces. The perfect circle it produced wasn't just a shape. It was proof that sometimes to achieve hard, geometric perfection, you have to work with something soft and flowing. The perfect circle from a water jet is static, but symmetry can spin. The stone itself can turn. The eighth method brought motion into the workshop, symmetry through rotation. Not a potter's wheel for clay, but something sturdier, adapted for stone. A simple rotating platform turned by a cord or a foot treadle, the ancient precursor to the lathe. Its purpose was a different kind of perfection, radial symmetry, where every point around a central axis is identical. For stone vessels, beads, seals, spindle walls, this was a revolution. The principle was simple: a roughly shaped stone, blank alabaster, serpentine, limestone fixed onto a central axle. The axle spins, the stone rotates. A carver holds a fixed cutting tool or a piece of abrasive stone steady against the spinning surface. The motion does the work. Any high spot gets worn down more than a low spot. The process guides the material toward a balanced circular form. Centering was everything. Any wobble in the mounting would ruin the symmetry, so they developed techniques. A pointed center on the axle, fitting into a small depression drilled into each end of the stone blank. It ensured the stone spun true, like a top on its point. The evidence is in the objects, an ancient Egyptian cosmetic palette for grinding pigments. Many aren't flat slabs. They're graceful, shallow bowls made of schist or basalt, with interiors ground into flawless concave curves. The concentric rings from the grinding tool are still visible, tracing the path of perfect rotation, or the thousands of stone beads found across the ancient world. Their perfectly spherical or cylindrical shapes, each one identical, point to a rotational process. A bead blank mounted on a thin axle, then shaped and polished as it spun, could be replicated endlessly. Even the spindle walls the stone waits for ancient looms. They're often beautifully shaped discs or domes with a central hole drilled with precision. It's likely these walls, tools for making thread, were themselves produced on the rotational devices they would later help to power. This method did more than produce objects. It influenced a visual language. The motifs it made possible, concentric circles, spirals, radiating lines, became decorative staples. A stone seal from Mesopotamia with a symmetrical star pattern. A Mycenaean gemstone carved with radiating petals. That's the artistic legacy of the rotary device. The carver could engrave into the soft stone as it turned, creating designs impossible to execute freehand with such balance. This was symmetry born from dynamics. The static art of stone met the rhythm of the wheel. Perfection found not only in stillness and plan, but in controlled, repetitive motion. The object became a record of its own creation, a frozen snapshot of a perfect spin. Rotation works for smaller things, but the truly monumental shapes, the massive foundation stones at Machu Picchu, the Cyclopean walls, their symmetry is too large for a lathe. For that scale, you need a different force, not a tool, but a transformation. They used fire and water to make the stone break itself. That's the ninth method. Thermal shock and spalling, a macro symmetry where the primary form comes from a controlled fracture, not carving. The principle is simple physics. Stone expands with heat, contracts with cold. Do that rapidly, unevenly, and the stress becomes a weapon, a precise one. Imagine ancient masons facing a granite outcrop. They want to split off a massive slab. They don't start with hammers. They build a small, controlled fire along the line where they want the split. They might use clay to contain the heat to a narrow zone. The surface along that line gets intensely hot, expanding. Then, on a signal, they douse it with cold water, or sometimes vinegar for faster cooling. The sudden, violent contraction of the hot surface pulling against the cool interior creates immense tensile stress. A clean crack propagates through the stone following the heated line. A thunderous pop and a perfect slab shears away. This wasn't guesswork, it was a managed risk. The artisans had to understand their material. Granite, with its crystalline structure, is particularly susceptible. The stone type was the first critical decision. They also had to control the rate. Too slow, and the heat diffuses, causing a messy break. Too fast, and the shock could cause uncontrolled shattering. It was a balance, a performance of applied physics. Archaeologist and materials expert Dr. Linnea Shaw has led experiments. Her teams used lines of charcoal fires and sudden water application. They could reliably split large granite and basalt boulders along straight planes. The resulting fracture face is often naturally flat and smooth. It required far less finishing work than pounding the stone away with hammers. A massive labor-saving innovation. The stone did the heaviest work. Look at those cyclopean walls in Greece or Peru, those gargantuan blocks fitted with precision. Their first, most critical symmetry, their flat, mating surfaces, may well have begun with a line of fire and a cloud of steam. This method provided the blank canvas. The gigantic, geometrically true slab that could then be fine-tuned. What's remarkable is the foresight, to see not just the stone, but the potential fracture plane hidden within it. To use fire and water in a precise, cooperative dance to reveal that hidden line. This wasn't destruction, it was a form of liberation, freeing a perfect shape from the heart of the mountain. A command whispered in the language of heat and cold. It turns the raw chaos of a breaking rock into a deliberate, symmetrical act, the birth of a monument announced by a crack of thunder they learned to summon. The stone cracks and then the chisel starts. That's a different kind of making, not splitting the rock but finding what's inside. In a temple cut from stone, a sculptor stands at a wall. They aren't adding anything, they're taking stone away layer after layer to pull a symmetrical world out of the flat surface. That's the 10th method, relief carving by step-back profiling. A dance of depth, the artist works from the future back into the present. The principle feels backwards. You don't start with what's closest, you start with what's farthest back. The sculptor defines the back plane, first the wall itself as the deepest point. Then they step forward. They carve the elements that will project the most. The highest points, a god's face in the center, the tips of headdresses, outstretched hands, these frontmost elements are locked in first. Their height sets the scale for everything behind. Only then does the carver step back, literally, figuratively, to the next plane of depth. They carve the shoulders behind the head, the torso behind the arms. Secondary figures behind the primary ones. Each layer recesses slightly further into the stone. Medieval mason manuals called this working from the face. Carving from the front to the back, preserving the intended perspective from the very beginning. The symmetry of the final scene depended on that sequenced discipline. A central axis line was incised deeply into the stone. That was the guide, as the carver worked on the left side, defining the curve of a warrior's forward leg. They would measure its projection from that central line. Then, moving to the right side, they'd replicate that exact depth, that exact distance. It wasn't just matching shapes, it was matching spatial presence. They used simple depth gauges, rods with notches, to transfer measurements from one side of the composition to the other. This systematic removal prevented a common disaster, undercutting. If you carved a deep background element first, you might later find you had no stone left to support the foreground figure meant to stand in front. The figure would be left hanging. Unsupported, it would break off. Step-back profiling eliminated that risk. The stone for the foreground was always preserved until it was its turn to be shaped. The grandeur of Angkor Wat's bas-relief galleries comes from this method. Miles of narrative stone, vast processions, mythological battles, all in breathtaking harmony. Row upon row of identical Apsara dancers, their arms arched in perfect mirrored curves, each figure standing at the same precise level of projection from the wall. That uniform depth creates a rhythm, a hypnotic symmetry across hundreds of feet. It feels like a single, endless moment, frozen in perfect balance, or the spiral narrative of Trajan's column in Rome. Thousands of figures in a detailed frieze, telling a military campaign. Roman legionaries march in formation, their shields held at the same angle, their helmets breaking the same plane. That visual consistency, that ordered depth, it was achieved by teams of carvers all following the step-back protocol. They could work on different sections at the same time, knowing that if they all respected the established planes of depth, every figure would slot into the collective scene with proportional harmony. How did this prevent distortion? By controlling the third dimension from the outset. A face carved this way doesn't end up with one eye bulging forward and the other sunken back. both eyes exist on the same plane. Because that plane was established before the finer details were touched, the method forced a holistic vision. The carver had to hold the entire finished scene in their mind, in all its depth before the first chip of stone fell. The symmetry they achieved wasn't just left to right. It was a symmetry of space, a perfect balance between what emerges and what recedes, giving stone the breadth and shadow of life. The step-back method gave them a world made of stone, but to keep that world from coming apart, they needed something else, a hidden architecture, a kind of secret stitching. That's what the 11th method was, precision drilling for inlay for joinery, where symmetry became a question of alignment measured in fractions of a millimeter. The goal was a seamless whole, a floor that looked like one single sheet of geometric pattern, a statue whose eyes seemed to hold a lifelike gaze. That perfection was an illusion. Built from many perfect parts connected invisibly, the tool was often just a bow drill, a hardened copper tip, loaded with an abrasive slurry quartz sand and water. But the real genius wasn't the drill, it was the guide, a wooden jig carved with holes clamped over the stone. That jig made sure every drill bit entered at a perfect 90-degree angle. And it spaced each hole at a precise, predetermined distance from the next one. That was the birth of repeatable precision in stone assembly. Take a checkerboard floor. Black and white marble, hundreds of holes had to be drilled into the base slab to accept the small, polished stone plugs that formed the pattern. Each hole needed the same depth, the same diameter, so every plug would sit flush, creating a perfectly flat surface, a seamless one. The drill bits themselves were consumable. A copper tube, its end packed with abrasive sand, would slowly grind its way down. As it wore, you'd resharpen it or replace it. The consistency in ancient dowel holes tells a story of remarkable process control. Studies of broken Egyptian statues show something. The dowel holes for attaching separate limbs, an arm to a shoulder, a crown to a head, they're not just aligned, they're countersunk, tapered slightly at the opening to guide the dowel home. And they often show microscopic striations from the abrasive, spiraling in a perfect, consistent pattern that indicates a steady hand, constant pressure. A meticulously maintained slurry, the inlay work took this further, to set a lapis lazuli eyebrow into a limestone face, or a carnelian sun disk into a temple wall. The cavity had to be carved with undercuts. The stone was shaped like a dovetail, wider at the bottom than the top. Then a matching piece of inlay material was ground to fit that complex negative space perfectly. A gypsum or resin adhesive locked it in place. Once polished, the joint vanished. The different stones appeared to grow from one another. This hidden joinery reaches its most haunting expression in the eyes. Hellenistic Greek statues, that uncanny, lifelike stare didn't come from painted stone. The eyeball itself was a separate sculpture, made of polished glass, ivory, or colored stone. A perfectly shaped sphere or disc. The socket in the statue's head was drilled and carved with immaculate symmetry to hold it. The eyelid was carved to curve over it with exacting precision. The result was a statue that seemed to see the symmetry of the gaze, the balanced reflection of light in each glass eye. That was achieved because the empty sockets themselves were drilled as a perfectly mirrored pair. It was an act of profound empathy, using mechanical precision to simulate the spark of consciousness. So what does this tell us, this meticulous, hidden stitching? The desire for a flawless surface went beyond beauty. It was a philosophical stance. The cracks, the seams, the joints, those were evidence of the made thing. Of assembly. By making these connections invisible, the artisans aspired to a higher ideal. They wanted the finished work to appear as if it had always existed. Whole, complete, a perfect geometric truth revealed, not constructed. The symmetry was no longer just in the pattern you saw. It was in the countless, unseen points of perfect alignment that held the illusion together. A testament to a belief that true mastery hides its own mechanics. The invisible joins held it all together, but the real test was always the light. The 12th method used the sun itself as a tool. They worked with shadow and light templates, an ancient kind of optical comparison. It was nature's own quality check. For a culture without electric lamps or lasers, the moving sun gave them a perfect parallel beam. The process was simple. A master would first make a perfect two-dimensional profile of the shape they wanted, cut from thin wood or hammered metal. That was the template. At a specific time of day, often mid-morning or mid-afternoon for that angled light, they'd place this template between the sun and the rough stone. The template cast a sharp, dark shadow onto the stone's surface. That shadow told the truth. Any bulge on the stone that stuck out past the shadow line was a high spot, needing to be cut back. Any dip that fell short was a low spot, still needing work. The carver's job was to remove stone, bit by bit, until the physical surface of the sculpture met the edge of that projected shadow. The stone would just disappear into the dark outline. Renaissance artists who used this later talked about following the sun's judgment. It was an impartial guide. You couldn't argue with the shadow. It showed asymmetry with a brutal, silent clarity. This method needed deep planning around the sun's path. For a large statue that might take months, they had to work at the same time each day to keep the light angle consistent. The changing seasons were a challenge as the sun's arc across the sky shifted. A master planner would account for that. Maybe having different set times for summer versus winter, or using a fixed feature, like the edge of a temple roof, to mask the sun and create a consistent shadow. They used both negative and positive templates. A negative template, a cut-out silhouette, cast a solid shadow of the form itself. A positive template, the reverse, cast a shadow of the empty space around the form. Each was useful for different stages. The negative template helped define the overall mass. The positive template was good for refining delicate details. Like the channels between column fluting or the recesses around a decorative rosette, take the fluting on a Greek column. Those vertical curves aren't just decoration. They create a play of light and shadow that makes the column seem lighter, more dynamic. Getting perfect uniformity in those curves from the top of a 30-foot column to the bottom would be nearly impossible by eye alone. But with a light template, a curved profile for the perfect flute, a worker could check the symmetry at every stage. They'd hold the template, catch the sun, and run the shadow down the length of the carved channel. Any deviation stood out immediately. This technique turned sunlight from a condition of work into an active participant. It was a collaboration between human intention and a cosmic constant. The carver learned to read the language of shadows, to see absence as a guide for presence. The final symmetry they achieved was, in a literal sense, written in light. A confirmation that their handiwork stood in perfect agreement with the geometry of the heavens. Light gave them the outline, but for the smallest treasures they needed a different wheel. Not for shaping, for polishing, a whisper of friction against stone to create facets that could catch light and split it. The 13th method was abrasive lapidary on rotary wheels. The high-precision craft of the gem cutter, where symmetry met brilliance in miniature. For seals, for cameos, for beads, perfection was a gleam, a perfectly flat facet. The tools were simple, a horizontal wheel, often lead or a fine-grained stone mounted on a spindle. The wheel was charged, coated with a paste of oil and an incredibly fine abrasive powder. They used Naxian stone, a natural emery from Naxos, rich in corundum. For the hardest gems, sapphire or diamond, they might use diamond dust itself, knowing one diamond could cut another. A hand crank or a bow mechanism kept the wheel spinning, steady, controlled. The artistry was in the holding. The tiny gemstone was fixed to the end of a dop stick with wax. The lapidary would press the stone against the flat, spinning surface, not with force, with a delicate, unwavering pressure. This ground a flat facet onto the gem. Mirrored, but one facet isn't symmetry. Symmetry is repetition. So came the crucial step, indexing. After grinding one facet, the craftsman would rotate the stone. By a precise, measured angle, they used simple wooden indexing blocks with notches or marks on the top stick itself to ensure each new facet was identical to the last. This is how they created the geometric intaglios of the Roman era, a profile portrait carved in negative into a gemstone, surrounded by a perfect border of repeating, angled facets. Pliny the Elder marveled at the process, describing how emery could wear away anything through patient abrasion. The work was a progression. They started with a coarse grit to establish the basic form. The facet angles then moved to successively finer powders, each removing the scratches of the last until the surface achieved a glass-like polish. The final test was the eye. When light hit the finished gem, it should return in a sharp, bright flash from every symmetrical plane. No dull reflections, no distortion. Look at a garnet bead from an ancient necklace. Its surface a series of tiny, flat facets in a perfect geometric pattern. That pattern isn't random. It often aligns with the stone's natural crystal structure. By orienting the gem correctly on the dot before cutting, the lapidary worked with the stone's grain, not against it. This implied a deep, intuitive knowledge of crystallography. Understanding that different directions in a crystal have different hardnesses, that symmetry in the final art was best built upon the hidden symmetry within the material itself. This method transformed jewelry into mathematical art. A carved carnelian seal with its mirrored design wasn't just a signature stamp. It was a testament to control on a microscopic scale. The lapidary wasn't just carving an image. They were engineering light, using geometry to trap brilliance and redirect it. In these tiny stones, the drive for perfect symmetry found its most concentrated expression. Luminous, the gem was silent, but stone can sing. The 14th method, it's about a forgotten dialogue between the carver and the material, guided not just by sight but by sound. Symmetry guided by sonic resonance, it's speculative but it's rooted in something true. We understand balance through vibration. The idea is simple. If you tap a stone bowl at different points, the sound tells you the thickness of the walls. A clear, uniform ring means the walls are even. A dull thud or a shifting pitch, that betrays a bulge. Or a weak spot, that could have been the music of stone, an auditory feedback loop for perfection. Picture a craftsperson shaping a vessel from a fine-grained basalt. A stone known for its bell-like ring. As they grind the interior, they lift the piece, tap the outer surface with a small mallet. They aren't just listening for a pleasant sound. They're mapping a high note here, a lower note there. The difference tells them where to remove more material. The goal is a chorus of identical tones from every point on the vessel. That sonic uniformity translates directly to symmetry, to structural integrity. It's a form of quality control that uses a different sense, especially valuable for hollow forms where you can't see the interior. This method wouldn't stand alone, it would work with others. A carver might use a light template for the external profile and sonic tapping to perfect the internal volume. The two techniques together create a vessel of harmony, inside and out. The resonance itself might become the purpose. Think of Tibetan singing bowls. Or certain ritual vessels from antiquity. Their ability to produce a pure, sustained tone that's not an accident of shape. It's the proof of their symmetrical perfection. The sound is the artifact of flawless geometry. This sonic sensitivity might extend to architecture. There are accounts from Roman times to the medieval period of certain columns in temples that were said to hum when struck. Often wrapped in legend, but it hints at a practical understanding. Builders may have selected columns based on their acoustic properties, knowing that a structurally sound, symmetrical stone would carry a specific vibration. A column that rang true was a column built to last. How would this auditory feedback guide the sculptor's hammer? It creates a conversation. Each tap asks a question of the stone. The pitch of the response tells the carver where to apply the next gentle blow or the next abrasive stroke. It turns creation into a call and response. A slow duet between human intention and the hidden physical song locked within the rock. The pursuit of balance becomes not just a visual ideal, but a harmonic one. The final masterpiece doesn't just look perfect. In the hands of its maker, it sounds perfect too. A single, pure note held in the palm, born from listening as much as from looking. A perfect note can be silenced. Stone lasts, but it isn't invincible. Weather, conflict, and accident, these things can break a symmetrical whole. So when a masterpiece is fractured, how do you restore its balance without erasing its history? That's the 15th method, plaster cast reverse engineering, a technique for restoration symmetry. It's a bridge built with care between the past and the present. You start with what's left. Conservators at a place like the Acropolis, they face a puzzle. A statue of a goddess may be missing an arm. The left side is intact, a perfect example of classical proportion. The right side is gone. The goal isn't to invent a new arm. It's to rediscover the original one, to give the sculpture back its intended symmetry. So they begin with the intact original. They apply a flexible silicone mold to the surviving left arm. That captures every contour, every fold of drapery, every subtle muscular detail. From that negative mold, they pour a special plaster or resin. It hardens into a perfect positive copy, a mirror of the original, but a left arm isn't a right arm. This is where the method becomes a kind of geometric alchemy. The plaster cast of the left arm is used as a master reference, not to copy directly, but to reverse. Craftsmen use a pointing machine, that three-armed tool, to take thousands of precise measurements from this plaster model. For each point they record, they have to calculate its mirrored counterpart. If a point on the plaster cast is 5 centimeters from the central axis of the torso, the corresponding point on the new stone must be 5 centimeters from that same axis but on the opposite side. This translation of data from left to right, that's the core of the restoration. It turns the existing half into a precise blueprint for the missing half. The challenges are deep. Material matching is the first. The new stone must not only look like the old, it must behave like it, whether at the same rate, accept the same patina. Conservators will often source marble from the original quarry if they can to ensure mineralogical harmony. Then there's the carving itself. Using the translated measurements, the carver roughs out the new arm. The final stage is the most delicate, the surface finishing. They have to replicate not just the form but the texture, the tool marks of the ancient artisans. The specific quality of the polish. This is where science meets art. The carver has to channel the original craftsman's technique, their touch, to make the new stone whisper the same language as the old. You see this in the reconstructed portions of the Parthenon frieze. Where original blocks were shattered, new marble has been carefully shaped using casts taken from surviving sections and from earlier, more complete drawings. The goal is visual harmony, to let the eye flow across the procession of figures without a jarring interruption, to restore the narrative rhythm. This raises a quiet question. When new stone meets old in the name of symmetry, what are we doing? Are we repairing history or creating a hybrid? Modern conservation philosophy is clear. The new work should be discernible upon close inspection, but not detract from the whole. It should support, not pretend. The join line is often left slightly visible, or the new stone is left subtly unfinished as a respectful signature of our time. So this technique, it's more than a method. It's an act of humility. It admits that while we can reconstruct the geometry, we can never fully reclaim the moment of creation. What we offer is a careful echo, a symmetrical compliment paid across the centuries, letting a broken song be heard again, complete, restoration is a careful echo. But creation is a dance of two hands moving together. The 16th method makes the carver's own body into a living instrument of balance. It's called the principle of bilateral reduction. A conceptual discipline, a kinetic approach to symmetry, the artist works on both sides of a central axis at the same time, removing roughly equal amounts of stone from the left and the right as the form comes out of the block. This isn't just a technique for the final details. It's a philosophy applied from the very first roughing out blows. The stone is treated as a mirrored entity from the beginning. In traditional apprenticeships, masters would drill this principle. A student might be given 2 mallets, 2 chisels, and told to develop a rhythm. Strike the left side, then the right. Step back, assess, then repeat. The goal was to keep the evolving mass centered, to feel the symmetry in the shoulders and the swing of the arms. It trained the body to understand balance through motion. Mental visualization is paramount here. Before any cut, the carver has to hold the finished, symmetrical form in their mind's eye. They see not just the positive shape of the statue, but the negative space that will be carved away around it. And they remove that space in mirrored increments. They use simple tools to enforce this discipline. A pair of calipers is constantly in hand. After carving a curve on the statue's left cheek, the artisan immediately measures its projection from the central axis. Then they transfer that measurement to the right side, marking the exact corresponding point. This constant back and forth comparison, this dialogue between the two halves, prevents the sculpture from ever becoming lopsided during its development. It never allows one side to get too far ahead of the other. You can see the legacy of this method in the powerful, balanced wings of a carved eagle from a Roman standard. Each feather row on the left is a perfect mirror of the right because they were likely shaped in tandem. Or consider the paired guardian figures flanking a temple entrance in Egypt or Mesopotamia. Their imposing, identical stances speak of 2 master carvers, or one carver working in this bilateral mode, ensuring each colossal foot was placed with the same authority, each arm carved with the same tension. This workflow does something subtle to the artist. It demands a physical symmetry from them. The repetitive, mirrored motions can influence posture, muscle development, even the way they see. It embodies the idea that symmetry isn't just a visual outcome to be checked at the end. It is the very process of creation. The rhythm of the work itself becomes symmetrical. A meditation in stone that teaches the hands to think in reflections. The body learns symmetry by moving, but the stone has to accept a final, perfect curve. To get that, they needed something as soft as a hand but as persistent as the tide. That was the 17th method, abrasive sandbag molding, a flexible answer for monumental softness. Think of a giant stone dome or the rounded shoulder of a huge Buddha. Chisels leave flat planes, facets. For a seamless curve, you need something that can hug the form. So they used leather bags, stitched tight, filled with abrasive sand graded carefully. Teams of workers would take these heavy, pliable pads and rub them over the stone. Wide, rhythmic, sweeping motions, the bag would conform to the surface, its abrasive load grinding down every high spot with a gentle, even pressure. It was polishing through intimate contact. The process went in stages. They'd start with bags of coarse quartz sand to remove the major tool marks to establish the basic curve. Then came a medium grit, maybe a finer quartz or crushed garnet, to smooth out the scratches from the first stage. Finally, bags of the finest powder. Crushed corundum, sometimes polished ceramic dust, that would bring the surface to a mirror-like finish. The control was in the hands, in the rhythm. To avoid flat spots, the workers moved in overlapping, circular patterns, never letting the bag rest too long in one place. A foreman would use a long, flexible template, a curved wooden spline, to constantly check the profile against the desired arc. Any deviation got focused abrasion right on that spot. The bags themselves were simple engineering. Made from thick, oil-tanned leather to resist wear, from the abrasive inside and the stone outside, the stitching was double strong, often waxed, to prevent a catastrophic failure, a costly spill of precious grinding material. Their size varied. Some were for broad, two-person strokes across a dome's expanse, others small enough for one person to refine the curve of a statue's lip. This method was essential for the serene curves of Buddhist stupas across Asia. These massive, bell-shaped monuments symbolized the dome of heaven, their perfect, uninterrupted curvature, meant to guide the eye upward without a single jarring edge, that was likely achieved through thousands of hours of this flexible abrasion. You see a similar principle in Baroque fountains, where stone seems to melt into watery shapes, and the perfect roundness of the stone spheres of Costa Rica. Their makers and purpose are a mystery, but they stand as a testament to what patient, conformal abrasion can achieve. Their near-flawless sphericity suggests a mastery of finishing where a rigid tool would fail. Now a complex curve, like where a statue's arm meets its torso. How did this soft tool handle that? The answer is in the bag's nature. It would naturally settle into the concave space. Applying pressure evenly across the whole contact area, by changing the stroke direction circular or following the form's flow, the workers could ensure uniform wear from every angle. This method brought a gentle, uniform touch to the most monumental forms. It was a partnership, human strength, and a tool that yielded, proving that sometimes to coax perfect symmetry from stone, you speak to it with a whisper of leather and sand. Leather and sand shaped those soft curves, but the eye can be a trickster, and the 18th method embraced that optical illusion, forced perspective carving. They deliberately sacrificed perfect geometric symmetry, not for error but for a higher truth, the truth of human perception. You have a statue. It stands 30 feet above you, its head tilted back to gaze at the sky. How do you make it look balanced? If you carved it with mathematically perfect proportions, a curious thing happens. From the ground, the head looks too small. The legs seem stubby, distance foreshortens, perspective warps, so the ancient sculptors mastered theatrical symmetry. They carved not for the plumb line, but for the single, sacred viewpoint of the worshipper below. They called these adjustments optical refinements. The calculations were precise. They measured the viewing angle from the intended spot, often the center of a temple courtyard. From that fixed point, they worked backwards. They deliberately exaggerated the upper parts. The head might be made slightly larger. The folds of drapery high on the chest were carved more deeply to cast stronger shadows from far below. Features against the bright sky, like a helmet rim or an outstretched hand, were given extra volume, all so that when light and distance did their work, the figure would resolve in the viewer's eye as perfectly proportioned, as harmoniously balanced as if it stood right beside them. This method is etched into the stones of the Parthenon. The figures that filled its triangular pediments, high above the Athenian Acropolis, were carved with these distortions. A horse's neck might be elongated, a reclining god's torso made broader, so that from the plaza far below, the entire scene would appear dynamic, yet perfectly composed. The symmetry was experiential, not absolute. You see it in the colossal statues flanking Egyptian temple pylons, those immense figures of pharaohs seated or standing. They weren't carved with the same proportions a human-scale statue would use. Their shoulders are broader, their facial features more pronounced, because they were meant to be seen from the end of a long, processional avenue by people looking up in awe. The carvers understood the audience's experience was part of the sculpture. The monument wasn't complete until it was seen from its intended place. It reveals a sophisticated psychology of perception. They knew mathematical perfection on the workbench could translate as visual imperfection in the real world, so they pre-corrected for it. they engineered the viewer's reality. This method prioritizes the lived moment of encounter over an abstract ideal. It says the symmetry that matters is the one that forms in the mind of the beholder. In that space between the stone and the eye, it was an act of profound empathy, bending rock to accommodate how we see, to create, from a specific, humble vantage point, the flawless illusion of divine balance. The eye sees a perfect illusion, but the hand has to make it. For the smallest lines, the border of a seal, a star on a wall, they needed a different pen. The 19th method used hardened metal scribers and straight edges. This was microsymmetry, the delicate handwriting of stone. When a surface was polished to a mirror finish, the last step wasn't carving. It was drawing. A master would take a bronze scriber, its tip sharpened to a needle point. They'd pair it with a ruler, a straight edge made of a harder metal. Sometimes a perfectly cured hardwood. The straight edge wasn't just a guide, it was a shield. Its hardened edge kept the scriber's point from gouging into it, so the line stayed true. With a steady hand, they'd drag the scriber along the straight edge, scratching a hair-thin guideline right into the polished stone. No ink, just a permanent, shallow groove. For curves, for circles, they used fixed radius compasses, a central pivot point and an arm with the scriber at its end. One rotation would etch a perfect ring. The preparation was everything. The stone had to be flawlessly smooth, level. Any bump would cause the scriber to jump and ruin the line's consistency. They'd often prepare the area with a fine abrasive polish, then sometimes dust it with a light powder, chalk or ash. This made the incised line stand out clearly as they worked. Look at a Mesopotamian cylinder seal meant to be rolled onto clay. Its surface is a miniature world. Complex scenes with borders of repeating patterns, interlocking diamonds, precise zigzags, chains of dots. The regularity of these lines under magnification is astonishing. They show no waver. That's the signature of a scriber guided by a template or a meticulously marked grid. The process built complexity from simplicity. They'd incise the primary framework first, the central axes, the outer boundaries. Then, using small reusable templates, a piece of thin metal cut into a star shape, a wave pattern, they'd trace the repeating motif. Each press of the template, each pass of the scriber added another layer. This network of scratched lines became the ultimate guide. For shallow relief carving, a chisel would follow these grooves, deepening them. For inlay work, the incised lines marked the exact borders where different colored stones would meet. The geometric panels on Islamic architecture, the star and polygon patterns that seemed to stretch to infinity, all began with this precise scribing on individual tiles. How did they prevent the tool from slipping? The answer is in the pressure and the polish. The scriber's point was not hammered, it was dragged. The artist applied just enough downward force to bite into the surface, but kept a controlled, fluid motion. The pre-polished stone offered consistent resistance. It was a skill of touch, feeling the stone's response through the metal. This method represents the draftsmanship of the ancient world. It was the final step before the irreversible cut, a moment of pure geometry etched with clarity. In these hair-thin lines, we see a mind thinking in perfect angles. In repetitions, a testament to the idea that even the grandest symmetry is built from a single, flawless scratch. A scratch becomes a petal, but a window of stone and light, that's 100 petals. That's the 20th method, symmetry through sequential modularity, the perfect piece repeated. It broke the impossible down into something you could do. A rose window, a geometric dome, a wall of interlocking stars. These weren't carved as one whole thing. They were a grand puzzle. Each piece was a manageable masterpiece designed to lock with its neighbor. It was assembly line thinking for monumental art. A master designer would create the full pattern on parchment. Then they'd dissect it. They'd find the repeating modules. A single pointed arch, a single 8-pointed star, a single vine with 3 leaves, that module became the new unit of perfection. They'd make a master template. From hardwood or sheet metal, that template was the law for dozens of stonecutters working in quarries miles away. Each carver got a rough block and a copy of the template. Their job wasn't to interpret, it was to replicate, to make one perfect, identical piece of the puzzle. Studies of Gothic records show this system in detail. For a cathedral like Chartres, the stone for hundreds of identical window pieces, the finials, the crockets, it was all pre-carved off-site using these templates. Each finished piece was often marked, a Roman numeral or a mason's mark, a code that told the builders exactly where it went. The joinery itself was a marvel of pre-planning. Stone dowels, mortise and tenon joints carved right into the edges. These weren't just for strength, they were alignment guides. A tenon on one piece would only fit the mortise on its specific neighbor. Like a key in a lock that guaranteed the overall symmetry emerged from the precise fit. Of course, stone is never perfectly predictable. The final act was the fitting. On the scaffolding, master masons would make tiny, last-minute adjustments. A slight rub with an abrasive stone here, a minor trim there to account for any microscopic variations. This fine-tuning was the final breath of human judgment into the mechanical process. The result is the hypnotic repetition of the Alhambra's ceilings. Those countless identical cells of honeycomb mucanas, each one a small vault multiplying into a cosmic fractal, or the endless geometric lace of Moorish arches. That seamless, expanding pattern speaks of a master grid and a single, perfect module, copied and mirrored into infinity. For quality control, the template was the first safeguard. But often, a master mason would use a simple gauge, a notched rod or a profile cut from metal. He would test random pieces from a batch. If the gauge didn't fit snugly, the piece was rejected, or reworked or set aside for a less visible spot. This method scaled human ambition. It meant a vision of perfect, complex symmetry could be distributed across a continent of workshops. It democratized precision. A carver in a provincial quarry following the master template could contribute to a symphony of stone he might never see finished. His perfect leaf would find its place in a vast stone forest growing toward the sky. The symmetry achieved wasn't just in the pattern you see. It was in the silent, distributed agreement among hundreds of hands, all guided by the same geometric truth. A consensus in stone built one perfect module at a time. They assembled that modular puzzle by sight and touch, but to see a work as a whole, sometimes you turn it upside down. The 21st method used the world's oldest mirror, a pool of still water, liquid mirroring. Before polished metal was common, you had a simple basin to hold a reflection. And that reflection became a tool. A carver would place a shallow dish of dark, still liquid near the work, water or sometimes oil for a more stable surface. In the right light, the stone's image would appear, inverted and perfect on that dark plane. This reversed view tricked the mind. The brain, familiar with the sculpture from one angle, would suddenly see it new. A slight dip in a cheek, an eye set a fraction too high. Flaws that direct sight had grown used to would jump out in the reflection. It was a deliberate disorientation for the sake of correction. The containers themselves were often simple works, wide, shallow bowls of polished basalt or slate, prized for their dark, non-porous surfaces. The carver needed absolute stillness. A drafty workshop was no good. They often worked in the calm air of early morning or late evening, or placed the basin in a recessed niche to shield it from breezes. The lighting was just as important. A single, angled light source, a high window or an oil lamp casting clear shadows across the carving. Those shadows would also reflect in the water, doubling the information. The liquid surface didn't just show form. It revealed the play of light and shadow, the balance of mass in a completely fresh way. This technique was more than a trick. It was a bridge between art and a kind of early optics. Some classical texts on sculpture mention the practice, not as a major tool but as a final check. A moment of quiet assessment, it complemented the tactile feel of the stone and the measurements of calipers. Where fingers could feel a ridge and eyes could measure a line, the reflection could judge the overall harmony. The quest for perfect facial symmetry in Hellenistic portrait busts, those lifelike faces, may have used this humble tool. A sculptor could stare into the liquid mirror, comparing the left side of the reflected face to the right side of the real one, a continuous loop of comparison. How does a reversed image alter perception? It breaks the tyranny of habit. When you work on something for weeks, your eye learns to compensate. It sees what it expects to see. The reflection presents the familiar as foreign. It forces a double take. That moment of surprise, that slight jar, is where the artist's critical eye re-engages. It's a method of seeing the work as a stranger would, or as the gods might see it, perfect and whole. This simple act of looking down into a dish of water leveraged a basic law of physics for artistic refinement. It turned a natural phenomenon into a quiet partner in the pursuit of the ideal, a tool born not from the forge, but from patience and observation, proving that sometimes the clearest vision comes from looking at things backwards. The reflection showed the whole thing, but to carve an empty space inside the stone, you had to draw with a line that wasn't there. The 20-second method used an abrasive wire for internal contours. It was a way to carve the air itself, to make symmetrical negative spaces inside a solid block, like the handle of a stone vase, a loop from the same piece of rock. Or those pierced screens in temple windows, stone turned into geometric lace. This was symmetry defined by absence, a clean, mirrored edge around nothing. The tool was simple in concept, a length of stiff wire, probably bronze. This wire wasn't a blade, it was a carrier. Workers would coat it with a thick paste quartz sand mixed with oil or water. That made a flexible, cutting strand. To start, they needed a gateway. They'd use a bow drill with an abrasive slurry to bore a small starter hole, right where the internal cut would begin. This hole was just big enough to thread the wire through. Once threaded, the wire's ends were fastened to a wooden bow or a simple U-shaped frame that kept the wire under tension. Tension was everything. A slack wire would bend, wander. It would create a wobbly cut. A taut wire cut a true, straight path, or a gently curving one. The artisan or a pair working together would pull the frame back and forth. The abrasive coated wire traveled through its own narrow channel, grinding away microscopic particles with each pass. It was a sawing motion, but the teeth were constantly renewed. You'd dip the wire back into the abrasive slurry. The process was glacially slow. It required a deep, quiet patience. You couldn't force it. Too much pressure would snap the wire, leave it trapped inside a half-cut block. That was a costly failure, so the rhythm had to be steady. Gentle, persistent, the symmetrical internal curve emerged over days, maybe weeks. You see the evidence in the artifacts, certain stone lamps from ancient India or China. They have complex fretwork cages carved from a single block. The cutout patterns show narrow, uniform channels with smooth, parallel sides. That's the signature of a thin, controlled abrasive strand passing through. This technique reaches a breathtaking scale in the stone windows of some Jain temples. Entire walls fashioned into screens of astonishing delicacy, elaborate geometric patterns. Swirls and knots and repeating stars, all carved from solid marble. The stone between the patterns is completely pierced, creating a play of light and shadow that is itself perfectly symmetrical. These weren't assembled from pieces. They were revealed from within a single, massive slab, with abrasive wires painstakingly navigating the intricate designs. It was the ultimate test of planning and control. How did they keep the wire on course for such long, complex paths? The answer is in the starter holes and guide channels. For an intricate pattern, they drill a series of holes at the key vertices, the sharp corners of a star, the turning points of a spiral. The abrasive wire would then be guided from hole to hole. Connecting the dots, the lines between these fixed points were maintained by the wire's tension and the craftsman's steady hand. It was a form of Stone Age connect the dots. Where the picture was a silhouette of light, this method represents a peak of confidence. It shows artisans who were so masterful, they were no longer intimidated by the stone's solidity. They could see the empty space inside it as clearly as the form around it. They could draw in 3 dimensions with a whisper of metal and sand, turning brute rock into something fragile and airy. And symmetrical, not despite the material's nature, but in a beautiful defiance of it, the stone lantern glowing from within, that became a symbol of the achievement. Light held captive by a cage of perfect, patient lines. The wire carved an absence, but some cultures filled that space with a different line, a line of law. The 23rd method was symmetry by cultural canon, by proportional rules, and this was perfection, but not as an artistic goal. It was a divine mandate. A religious law, an aesthetic law written in mathematics. Cultures from Egypt to India, they developed these exhaustive rule books. The Egyptian canon used a grid. 18 squares from the hairline to the soles of the feet. The Indian Shilpa Shastras prescribed the Tala system, a unit of measure based on the width of a finger. These weren't suggestions, they were scripture for the sculptor's hand. The Shilpa Shastras stated plainly, measurement is the root of all form. These texts gave exact formulas. The length of a nose should be 1 tala, the space between the eyes 1/3 of a tala. The height of a temple doorway had to be twice its width plus 1/4. Every relationship was predetermined. The rules left almost nothing to artistic whim. They encoded a cosmic order into physical form, and training was a process of internalization. An apprentice didn't just learn to carve, they memorized ratios, they practiced drawing the canonical grids until their hands moved by instinct. They used standardized measuring rods, often inscribed with the sacred units. The master would check, but not for beauty. They checked for adherence. Was the navel exactly at the 11th square? Was the distance from knee to heel precisely 1.5 times the length of the foot? This discipline produced a civilization's visual signature. The serene, uniform faces of Khmer deity statues, from Angkor Wat to distant provincial temples, they share an unmistakable harmony. That's not one artist's style. It's the output of a shared, rigorous system. A system that ensured a god carved in the capital and a god carved in a frontier workshop would be recognized as the same divine presence. The symmetry was theological. It guaranteed the deity's form was a perfect vessel for its essence. So what's lost when creativity is bound by such strict rules? Perhaps individual expression, the flash of unique genius, but what's gained is something profound, a collective visual language, a stability of meaning across centuries. It made symmetry a cultural signature, as recognizable as a written alphabet. The rulebook turned the artisan into a priest of geometry. Their task wasn't to invent a new ideal, but to faithfully replicate an eternal one. The resulting art feels timeless, but not by accident. It's by design. It speaks of a world where beauty was understood not as a matter of taste, but as a demonstrable mathematical truth. The rulebooks gave them divine proportions, but the canvas was a valley. The 24th method was for symmetry on the scale of the land itself, a sighting technique. Ropes and stakes, this was geodetic symmetry, a way to align massive stones across miles of rolling hills, to connect earth and sky in a single, monumental gesture. At Carnac in Brittany, thousands of standing stones march across the landscape, rows so straight they defy the uneven ground. This wasn't random placement. It was a feat of prehistoric surveying, a macro architecture. It required a master plan and a communal eye. The process began with a celestial anchor. A master surveyor, someone with deep knowledge of the sky cycles, would choose a starting point, a point tied to a solar event, the rising sun on the summer solstice, or the setting moon at a major standstill. They'd drive a central stake into the earth at this sacred point. This stake was the pivot of their entire design. From it, they'd establish a primary baseline, a long, taut rope made of woven plant fiber or leather, treated for consistency, stretched out and anchored with another stake. This rope defined the first true line, the foundation of all that followed, but the ground is never flat. To maintain a straight sight line over a hill, they used a simple tool. Two tall, forked stakes. A worker would hold one stake at the starting point. A second worker, carrying another stake and a length of rope, would walk out until they were just out of sight over the rise. They'd raise their stake high. The first worker would signal left or right until the top of the distant stake aligned perfectly with their own sighting point, and perhaps a landmark on the far horizon. Once aligned, the second worker would plant their stake. This created a new point on the invisible straight line, now corrected for the intervening hill. They'd repeat this process, leapfrogging across the terrain, creating a chain of sighting points that traced a perfect geometric line over the natural curves of the earth. For parallel rows like the avenues at Carnac, they used a standard unit of measure, a rope of fixed length. From each point on the master line, they'd measure out perpendicular lines using a simple 3-4-5 triangle method, tying knots in the rope at specific intervals to create a perfect right angle. This allowed them to mark out the positions for dozens, even hundreds, of parallel rows of menhirs. Each stone's planting site was marked with a small stake. Teams then quarried and transported the massive stones to these preordained points. The communal effort was staggering. It required not just muscle but a shared understanding of the plan, a trust in the markers left by the surveyors, the near-perfect alignment of the avenue leading to Stonehenge, a processional path marked by parallel ditches and banks, almost certainly required this technique. Over a distance of nearly 2 miles, the builders maintained a consistent width and direction, guiding the eye and the foot toward the sacred circle. How did they account for the subtle curvature of the earth over such distances? They may not have needed to. Their sight lines were local, connecting terrestrial points to celestial events on the horizon. The curve they corrected for was the topography directly in front of them. The hill, the valley, the grove of trees. This method transforms our understanding. The rows at Carnac are not just a collection of stones. They are a single, drawn line. A line of intention scored into the landscape by a society that could think in miles and generations. The symmetry achieved was between the human order of measured rope and the divine order of the sun's path. It was a way to make the land itself participate in a ceremony of alignment, to weave the chaos of nature into a pattern of profound geometric meaning. The stones stand as permanent witnesses to a day when the whole community looked down a line of sight and saw not just a distant stake, but a connection to something eternal. The final symmetry didn't come from a tool, it came from inside the carver. After years of using grids and templates, a master's hands just learned to move without them. That's the 25th method, the most human one, symmetry through practice, through kinesthetic memory. It's where technique dissolves into instinct. The body itself becomes the instrument of balance, embodied symmetry, where skill becomes second nature. An apprentice would start by copying, not creating. They might spend a year, maybe 2, just carving acanthus leaves over and over from the same master template. The goal wasn't one perfect leaf. It was to make the motion of carving that leaf part of their muscle memory, to train the nerves and sinews until the curve of the chisel, the angle of the mallet, the resistance of the stone, all of it felt as natural as walking. That built a neuromuscular map, a deep, physical understanding of form that lived in the hands, not just the mind. Meditation and focus were critical. In many traditions, carving was a form of moving meditation. The repetitive motion, the sound of the tool, the feel of the material, that intense focus quieted the conscious mind. It let the trained body take over. The carver entered a state of flow where thought and action merged. In that state, the symmetry wasn't calculated. It was felt. It came from a profound familiarity with both the material and the ideal form held within. That explains the flowing drapery folds carved by a Gothic master mason. The stone robes on a cathedral saint, they cascade with a natural, rhythmic grace. Each fold is unique, but together they create a harmonious whole. That lively symmetry could never come from a rigid template alone. It came from a hand that had carved 1,000 folds, a hand that understood how cloth falls, how light catches a ridge, how stone can be persuaded to mimic softness. That subtle vitality is the signature of ingrained skill. Can true artistic vitality exist without this internalized balance? Maybe not. The earlier methods guaranteed accuracy, a flawless geometric truth, but this final method breathed life into that geometry. It allowed for slight, intentional variations, the things that make stone seem to breathe. A leaf might curl slightly more on one side, as if responding to a breeze. A smile might be softer on one lip. Those aren't errors, they're evidence of a living artist working with a deep, physical wisdom. The ultimate tool, refined over a lifetime, was the artisan themselves. Their own body, mind, and spirit synchronized through endless practice. In their hands, the pursuit of symmetry transcended measurement. It became a kind of dance, a silent dialogue between human intention and the waiting stone. That final mastery, it comes from the body itself, and it shows something deeper. Those 25 methods we've followed, they aren't just a list of lost skills. They're parts of one story, a global story, about how humanity learned to speak with stone. Using the language of perfect balance, when you look past the individual techniques, you start to see principles, overarching ideas. They connect the Egyptian grid to the Greek pointing machine, the fire-cracked megalith to the gem cutter's lathe, and they show us the drive for symmetry was never just technical. It was a worldview, a philosophy carved right into the granite. At the core was this radical integration, observation and mathematics fused together. These artisans were relentless observers. They watched sunlight and shadows. They saw how water wore down rock, how a plumb line found true vertical. They didn't just see the world, they measured it, and they turned those measurements into repeatable geometry. The grid, the template, the proportional canon, these were tools for turning observed truth into mathematical law. That marriage of eye and number changed everything. It transformed intuition into a system, made perfection a shared goal, something achievable, not just a fleeting moment of inspiration. This pursuit demanded a patience we can hardly grasp now. The diorite pounder tapping for a year, the abrasive wire sawing for a month to free a single curve, that was a timescale in harmony with the stone itself. They knew rushing nature led to fracture, to flaw. Their patience was a form of reverence, an acknowledgement. To coax a perfect form from the mountain, you had to move at the mountain's pace. This wasn't inefficiency, it was a different calculus of value, where the endurance of the object justified the epoch of its creation, and that endurance was everything. Because symmetry was tied to beliefs about cosmic order, social order. For the Egyptians, perfect geometric alignment in a tomb, it wasn't just aesthetic. It was a metaphysical necessity. It made sure the journey through the afterlife would be stable, ordered, eternal, a reflection of the unchanging stars. Their symmetry was a bulwark against chaos. For the Greeks, symmetry in the human form represented the ideal citizen, balanced in body, mind, and spirit. Their search for perfect proportion in sculpture was a search for the divine potential within humanity. Different cultures took these universal principles and adapted them to their own materials, to their own spiritual needs. The Egyptians, with their hard granite and a religion focused on eternity, developed methods for immovable, timeless precision. The Greeks, with finer marbles and a philosophy of human excellence, refined techniques for idealized, lifelike beauty. The Khmer, building for the gods in sandstone, used canonical rules so every temple spire, every deity's smile, resonated with cosmic harmony. The same fundamental drive to create balance manifested in uniquely glorious ways. So this global story is really one of human ingenuity, answering a deep, shared impulse. The desire to create perfect, enduring forms in stone, it's a thread woven across continents and millennia. It tells us something. Before we split the atom or coded the digital world, we mastered a different kind of code. The code of angle and curve, of shadow and line. We learn to make the tangible world reflect an ideal one. In the silent, symmetrical face of a statue that's watched 1,000 years pass, you don't just see a skillful artist. You see a mind seeking order, a hand building stability, a spirit trying to touch something timeless through the patient, perfect arrangement of stone. That patient conversation with stone, it echoes across thousands of years, from the rhythmic pecking of diorite pounders to the guidance of shadows, to the use of sound. And what you find is a truth. These artisans weren't primitive, they were problem solvers. Their pursuit of symmetry was a blend. Art and science and spirit. We've walked through their workshops, the monumental ones, the minute ones. Their methods came from observation, deep, patient observation. Of sunlight, of water, of the grain in the rock itself. Each technique was an answer to a single, relentless question. How do you make a vision permanent? How do you make it balanced? How do you make it true? And that legacy, it challenges you to look at ruins differently, a fallen column, a silent statue, a geometric pattern on a broken wall. These aren't just remnants, they're textbooks. Each one holds chapters, chapters of advanced knowledge, written in the language of tool marks. Written in perfect angles, they speak of a time when innovation was measured in generations, when mastery was a covenant between the hand and the material. And it leaves you with a deeper respect for the hands that knew the weight of a mallet after 10,000 swings, for the minds that could hold a complex form in imagination and translate it point by point onto a mountainside. They shaped the world not with brute force but with an intelligence that feels familiar and also profoundly distant. Their drive to create order, to reflect cosmic harmony in a tangible form, it connects their age to ours. We're left with their silent questions. Etched in granite, etched in marble,